So now we're going to continue with chapter 9 in David Klein's organic chemistry book. The topic of this is alkynes. So here's what we're going to discuss. Introduction to alkynes, the nomenclature, the acidity of acetylene and terminal alkynes, the preparation of alkynes, reduction of alkynes. That will be during this video. And then the next video we'll finish up the chapter hydrohalogenation, hydration, halogenation, ozonolysis, alkylation, and some synthetic strategies. So the next video will be all about the reactions, and this video will be a little bit about the reactions and some about alkynes themselves. So here is a list of the alkynes, reactions. This will help you to study for them. And this is more or less in the order of how they will be covered in this chapter. So also you need to look at the preview and review video that I made for you at the beginning. You should look at that before and after each video for the alkenes chapter and for alkynes chapter, and the other chapters that cover reactions, because I'm telling you in those videos how to group the reactions together according to their mechanisms or the products that they form or the reagents, and being able to group them together in all of those ways will help you learn them and help them help you remember them, and you won't have to resort to just sheer memorization. So alkynes, you know that alkynes have a triple bond. One bond will be a sigma bond, and that's the sigma bond, of course, is going to lie directly in between the two carbon nuclei. And then you're going to have a pi bond above and below one plane. And so here you can see the overlap between these two red orbitals and these two blue orbitals. That constitutes one of the two pi bonds in an alkyne. And so the p orbitals that are overlapping are going up and down, and they're parallel with each other. And so you have this sideways overlap that constitutes a pi bond. The sigma bond is end-on. This pi bond is sideways. And so you have this other set of p orbitals going in and out of the plane of the screen, and they are also overlapping sideways. And you can see that that's the second pi bond. So here is one of the p orbitals, and here's the other p orbital that's overlapping to constitute one pi bond, and then the other pi bond is the orbitals that are going up and down. So that's the triple bond. You can see those. And here, this shows you the electron density map, the charge density map, and here you can see that the area of the triple bond is really electron rich, which is what you would expect, because you have the pi bonds here, and remember, pi bonds are not directly in between the two nuclei, like the sigma bond is directly in between the two nuclei. And so the pi bonds are more outer lying, they are higher in energy, those electrons are more loosely held, and so that is why you have the pi electrons reacting, but the sigma electrons are not reacting. And so this is going to be a center of electron density, high electron density. And alkynes in the industry and nature, you can see them, in natural products. And so here are a couple of terminal alkynes. I don't think that you need to memorize this, but this is just to convince you that you do indeed find alkyne linkages in naturally occurring compounds. Acetylene is very commonly used in industry, and you may have actually used an acetylene torch yourselves. Here's a synthetic alkyne, ethynyl estradiol, and you can see again, the terminal alkyne. It's the active ingredient in a lot of birth control pills. You will not need to memorize this structure or this molecule, but you should be able to see and recognize the alkyne linkage. So alkynes, notice that you have the Y here that is emphasized and the A here that is emphasized. So you're going to have to work not to confuse alkanes, alkenes, and alkynes. So the only thing differing in those names is one letter, A, E, or Y. And so alkynes are named using a lot of the same rules that we learned already for alkanes, and so I'll go through these, and they're very similar to alkenes, the alkene nomenclature as well. And so, once again, you identify the parent chain, and it must include the highest priority functional group. The chain, the parent chain, must include the highest priority functional group. And so we're going to look at some in which the carbon-carbon triple bond is the highest priority functional group. As functional groups go, triple bonds are rather low in priority, and you'll see that later on in alcohols and in carbonyl compounds. So, but for now, we're going to look at naming alkynes. So you identify and name the substituents just as before. You assign a locant to tell the position of each of the substituents, and you must give the highest priority functional group the lowest number possible. The highest priority functional group. So if it were an alcohol, you would give the hydroxyl group the lowest priority, the lowest number possible. But here we will number the parent chain in a way to give the carbon-carbon triple bond, because the ones that we look at, the carbon-carbon triple bond, is going to be the highest priority functional group. So, and then you list the numbered substituents before the parent name in alphabetical order, ignoring the prefixes except iso and neo when ordering them alphabetically. The carbon-carbon triple bond locant is placed either just before the parent name or just before the YNE suffix. I would urge you to learn it so that you're placing it just before the YNE suffix, although you'll have to be able to recognize it either way and know that it can happen either way. Because when you start to have multiple functional groups, you will be forced to put the locant for the triple bond just before the YNE in order to avoid confusion. So here's some examples. So for example, pentane, pentene, pentyne, and in both of these cases, the functional group is at the terminal position. And so here you can see that this is a comparison. So if you had this compound with no unsaturation in it, no double bond or triple bond, so your longest functional group, your longest parent chain would be 1, 2, 3, 4, 5, 6, 7, 8. So this would be octane. And you have this same molecule. Notice these are identical, except right here, there is no unsaturation, and yet here you have a triple bond. And so you no longer just look at the longest chain. You now look at the longest chain that contains the functional group. And this is the only functional group. So you're going to use the alkyne here. So we'll start numbering in a way that will give the alkyne functionality, the triple bond, the lowest possible number. So 1, 2, 3, 4, 5, 6, 7. So you don't start over here because you want to have the lowest possible number assigned to the functional group. So this is going to be a heptine, and you're going to start numbering up here. Now look at identify and number the substituents. So you assign a locant to the substituents. Let's go back and look at this one. We'll finish this one. So here, this would be an alkyne that starts at the 1 position. You don't have to say 2 because it's only 2 carbons long. So as soon as you specify 1, you know that the other carbon involved in the triple bond is number 2. You don't have to specify it. And so here we have a propyl group, and this is at the 1, 2, 3 position. So this is going to be 3-propyl hept-1-ine, or 3-propyl 1-heptine. Now, these are other molecules, and so these 2 molecules are the same. It just shows the different ways to number these. And so you can start numbering them in order to have the alkyne functionality with the lowest number. So 1, 2, 3, 4, 5, 6, 7. So here the triple bond starts at C2, or you can start numbering at the other end, 1, 2, 3, 4, 5, 6, 7. And the triple bond would start at carbon 5. So this one is correct because you want to have your highest priority functional group assigned the lowest number possible. So this one is correct. And so let's see if they number, if this is named. Yes. So you list the numbered substituents. So we have 2 methyls at 5 and another methyl at 6. So this is going to be a trimethyl, and its positions are 5, 5, 6. So 5, 5, 6 trimethyl, 2-heptine, or it can be hept-2-ine. If you only have the 1 functionality, there will be no confusion here. But if you have more functionalities where you have to add additional functional groups at the end, then you'll need to name it like this and put a locant before the name, the suffix for designating each functional group. So be ready to use either system. This seems a little easier because you haven't broken up the word heptine. But if you've got 2, 3, 4 different functional groups, you have to put the locant before each functional group suffix. Now, common names, methylacetylene, and here diisopropyl acetylene, phenylpropyl acetylene. So the ethyne, indicating 2 carbon atoms and a triple bond, is also acetylene. So, and you can, this is the common name system. Alkynes are also classified as terminal or internal. It's terminal if the triple bond is at the end, internal if the triple bond is in the middle. And terminal alkynes have a lower pKa than other hydrocarbons. So this is significantly lower. So that tells you that this proton is much more acidic. It's fairly acidic for an organic compound. So notice ethane has a pKa of 50, ethylene is 44, and acetylene is 25. That's quite a bit more acidic. And so you have to get used to expecting that the proton attached to a triple bond is rather acidic. It can be deprotonated by a strong base. And so here you have the base coming in, picking up the proton, a pair of electrons moving back and residing on carbon. And remember the REO. This explains why the acetylene is a stronger acid than, say, ethene, ethylene, or ethane. And so remember the REO, the O stands for orbital. Remember? Atom, resonance, induction, and orbital. You'll have to remember the REO, or at least it will help you a lot if you can remember it. The acidity of the terminal alkyne. So look at the sp3 hybridized orbital. You can see that it's sort of, actually when I envision it as a little bit thinner, longer and thinner. And so this is the sp3 orbital. This is where the, without the back lobe, of course it's going to have back lobe. And so this is where the pair of electrons would reside in an ethynyl anion. And so ethyl anion, sorry. So this is where the lone pair would reside in an ethyl anion. And you can see that this orbital lies pretty far out from the nucleus, okay? It's far out from the nucleus, and that's going to make it higher in energy. The tighter it is, the closer in it lies, the lower in energy and the more stable it will be. Now look, this is the ethynyl or the vinyl anion, and you can see that it is shorter, it lies closer in. This one is thinner and lying farther out. This one is more round. This is an sp2 hybridized orbital. This is sp3. This has more s character. This is 1 part out of 3. This is 1/3 s character. This is 1/4 s character. So this is shorter and fatter, like an s orbital. And so since it lies closer into the nucleus, it is more stable. And so that's why a vinyl anion or ethynyl anion would be more stable than the simple ethyl anion. And when you move to the pair of electrons residing in the sp hybridized orbital, where this is the ethynyl anion, you can see that this orbital is 50-50 S and P. So this is 50% S character. It's half S character. And remember, the S orbital lies close in to the nucleus. It's rounder. And so the pair of electrons would be held a lot closer into the nucleus, and it's going to be more stable. And so that's why this anion is much more stable than the others. That is the reason for it being a stable anion. And so this helps explain it to you. And if you remember this, you will remember the trend. It will be easy to remember. It's all related to the stability of the orbital that the lone pair resides in. This is more S character, lying closer into the nucleus, and therefore more stable. So the acidity, let's look at this. Now here we have a very strong base. This is sodium amide, okay? Sodium amide. Amide is NH2 minus, and this is a very strong base. That's because that ammonia is a very weak acid. So there's a huge tendency for this base to pick up a proton and become this very stable acid, this very stable molecule. This is a strong acid relative to ammonia, NH3. And so this acetylene or ethine will give up a proton to this strong base so that the strong base can become ammonia. So this comes in, plucks off a proton, the pair of electrons moves in to reside in an orbital on carbon. And here you can see it. You can see the anion with the lone pair residing on carbon. And so this is a weaker base. It's a weaker base than amide. Okay, amide is a strong base. This is a weaker base. And so this is a more stable system where you have the amide protonated, and you have the acetylene has given up its proton. Okay, and notice that the arrows show indeed that the equilibrium lies to the right. Here, on the other hand, you have the opposite, where the equilibrium lies to the left. You have a weaker base. Okay, this is a strong base. This is a weaker base than the acetylide. And so now you have the acetylide will pluck a proton off of water, and it converts this to hydroxide and acetylene. And so you have the equilibrium lying to the left because these are more stable. This is a weaker acid than water. This is a weaker base than acetylide. And so you have the system lying to the left. So this is getting the concept that any terminal alkyne, so this is an alkyne that's going to have a CH bond at the end, can be deprotonated by a base that is suitable or strong enough. And so sodium amide is often used as the base, but you can have others as well. So here are some others that could be used. These are three. So this is an alkyl anion. This is the amide. This is H minus. Any of these would deprotonate acetylene and give you acetylide. Okay, and that's because these conjugate acids are not strong acids at all, and it is more stable for these bases to be protonated and lead to acetylide than for acetylide to protonate any of these. This would be going uphill for acetylides, energetically uphill for acetylide to deprotonate any of these acids because they're such weak acids. These bases will not deprotonate the terminal alkyne. These are listed in order of base strength. And so you would be going energetically downhill to have acetylide deprotonate these alcohols or water and give you these oxygen anions. Alkynes, this is a preparation of alkynes. Now, alkynes can be prepared by elimination. So you need a dihalide. So here you can have a strong base, remember an E2 reaction. And so you can have a strong base come in and deprotonate, the pair of electrons moves in, you lose bromide, and you will get an alkene. Similarly, if you have a dihalide, you can have the strong base come in, deprotonate, the pair of electrons moves in, and then you lose Br, and then the second equivalent of strong base would come in and deprotonate. You get another double bond and lose bromide again. It is a stepwise reaction. You don't lose both bromides simultaneously. You have two separate E2 reactions to give you the alkyne. Now notice here, one equivalent of base would be sufficient. Here you'll have to have two equivalents of base because you're going to effect two E2 eliminations. So here this is showing you the first step. You deprotonate, form a double bond, lose bromide. Now you have the bromoalkene. Then your next step, you deprotonate, form another pi bond, and lose bromide to give you the alkyne. And so this is a geminal dihalide, geminal meaning that the two bromine functionalities are attached to the same carbon, geminal like twin substituents, and vicinal meaning that they are on carbons next door to each other. So this is a vicinal dihalide, this is a geminal dihalide. And here you can have two E2 eliminations by two equivalents of strong base First you would deprotonate, form a double bond, lose bromide, then you would deprotonate again, form another pi bond, and lose bromide. It's going to be a stepwise reaction, just like the one above. Each of these would be a stepwise reaction, and they have similar mechanisms. So excess sodium amide is often used, and that means that once you get the alkyne, if it's a terminal alkyne, it will also deprotonate and give you the alkynide ion. So you'll use two equivalents to do the E2 eliminations, and then if you have excess in there, you'll remove some of the alkynyl proton. So then, in order to get this back, if you do indeed want the alkynyl proton on there, you have to add a little bit of water to neutralize the reaction and protonate this. And so often you'll see, the reaction carried out and then some water added to take you back to the alkyne. And so this is very, very common. And this sort of step in here is often in a synthesis where you wind up with the anion and you have to add a little water to protonate the anion and get this, the desired alkyne. Often this sort of a reaction is just included in a general phrase called workup. They won't even, often in a synthesis, they won't even show this. They won't even show the water. They'll just use the term workup, and you're supposed to know what that means. And so, here it is, excess sodium amide in ammonia, and you form the alkynyl anion, and then you add some water as workup and protonate the terminal carbon to give you the alkyne. So this is the way that a reaction that you saw on the previous transparency would be drawn. So you can, now we're getting into some of the reactions, and so you'll have to be able to remember these. So these are the reactions, those were the syntheses of alkynes, and they're very important, but they're pretty simple, and you've had the E2 reactions, and so you'll be able to remember those. Now we're getting into the reduction of alkynes. In the reduction, of course, what you're doing is you're adding H2 across the pi bond. And so you will have some reactions in which you add H2. You just add one equivalent of H2 and you form the alkene. In some reactions, this one that has the poisonous catalyst, it's a weak catalyst. And there are multiple examples, Lindlar's catalyst. This nickel boride complex, that's another poisoned catalyst. And by poisoned, they mean weakened catalyst. And you don't need to get too much into that, but just remember that what that means when you see poisoned catalyst or Lindlar's catalyst, what that means is it's going to stop at the alkene. You're not going to add another equivalent of H2 across this pi bond. Remember that you saw in the reactions of alkenes that catalytic hydrogenation, adding H2 with a metal catalyst, would take you to the alkane. Well, here that's not the case. This one with a poisoned catalyst, a weakened catalyst, is not going to go all the way to the alkane. It will stop at the alkene. It will not reduce the alkene. Now, you're going to have some of these reactions that will give the cis alkene, like this one. This one will give the cis alkene, because what happens is the H2 and the pi bond both become complexed to the catalyst. And so the H2 adds to the pi bond while they're both complexed. And so it is a syn addition to give you the cis product. You won't always have the cis product. In some cases, you'll get the trans product in other reactions. And in some cases, the catalyst will be strong enough so that you'll go all the way to the alkane. So you're going to have three different types of reactions. One of these hydrogenation reactions will stop at the cis alkene. Another one will stop at the trans alkene. And another one will take you all the way to the alkane. And you'll have to be able to remember all three. And what will differentiate all three will be the reagents. So you'll have to keep the reagents in your mind. You'll have to pair the reagent with the product to be able to remember, exactly what you're getting, what each reagent will give you as the product. And so when I said the poisoned catalyst, it catalyzes the first addition. So it reduces the energy of activation of the first addition. So you have the first equivalent of H2 add across the triple bond. It follows this lower energy pathway. And then the second addition of H2, which would give you the alkane, does not provide a lower energy pathway. So the catalyst does not catalyze this next reaction. And so it stops at the alkene. And so the poisoned catalyst, you'll just have to remember that. You'll just have to remember that the poisoned catalyst stops at the alkene, and also those examples that I gave you, they contain a metal atom. You have a metal, your palladium here, or nickel. They contain a metal atom that your reactant, the alkyne, and the H2 can complex with. And so you get the syn addition. That's the way to remember it. It's from the mechanism. Dissolving metal reduction. So notice you don't have a transition metal. You have sodium, and sodium is too small to be able to complex anything to it, really, anything significant. So with here, you look at these reagents, the only metal you have is sodium. You're not going to have anything complex to sodium, yet these reagents do affect addition of H2. They affect hydrogenation to the of the alkyne, and so you're not going to have a complexation because this metal's too small, and so you're not going to have a syn addition. What you have is you have a reaction that gives you a trans or anti addition and the trans product. So that will help you remember this. And these reagents do not affect hydrogenation of alkenes. They only affect hydrogenation of alkynes. So you have two different hydrogenation reactions so far. You have the one to give you the cis product because you have a transition metal in the reagents. Here you have one that will give you an anti or the trans product because this affects a reaction, no complexation. It does not have a transition metal in the reagents. So now that's two of the different possibilities that I named earlier. So this proposed mechanism, and I don't think you'll ever see any part of this mechanism on any exam, but your book does spend a lot of time going over it, and so we'll go over it here. And so notice that this is a radical reaction. Okay, this is a radical reaction. It's called a dissolving metal reduction. And so what you have, notice that all of these arrows, oh, not all, but in this first step, the arrows are all single barbed arrows, indicating it's a radical reaction that's taking place. So sodium metal has a strong tendency to give up an electron and become Na plus sodium cation. And so it does indeed give up an electron to the alkyne. And so you have now the alkyne anion, where the pair of electrons now constitutes a positive charge, which deprotonates ammonia. Okay, and you have the unpaired electron left over here, and sodium metal adds another electron, so that once again you have another anion, and it deprotonates ammonia again. And so you have sodium donating the electron and ammonia donating the proton. And so now you have added the hydrogens to the two carbons in to give you the trans product. And the trans product is favored because, well, for two reasons. Sterically, the alkyl groups are farther apart, but also back here, if you go here, if you look at this, these two orbitals are pointing away from each other because they contain electrons. And so you're going to have electron density in both of those orbitals, and there will be a tendency for them to get as far apart from each other as possible. So you've got both of those things happening, sterics and electronic effects. And so here's the first step, which we've already covered, donation of an electron. Notice the single barbed arrows indicating movement of a single electron. Now, this is the same mechanism I just went over. The previous transparency was a summary. These are the steps one by one. And so now, notice you have steric effects. These two alkyl groups are as far apart as possible. These two orbitals containing electrons are as far apart as possible. So this is giving you the trans, what's going to become the trans product. And so the stereochemistry that will become the trans product. And so the next step is this orbital containing two electrons is going to abstract a, this is just more explanation of the trans product. This is lower energy, less sterics, less electronic interactions. Here you'll have repulsion, and here you'd have steric effects. So now the next step is for the pair of electrons to remove a proton from the ammonia. And so you have the trans product. Now, reduction of alkynes. This is the summary. This is the summary. So you have the Lindlar's catalyst. This is the poisoned catalyst. Remember, there is a transition metal contained in this catalyst here, and so this is catalytic hydrogenation. It stops at, this reaction stops at the cis alkene. Then you can have the dissolving metal reduction. Here you do not have a transition metal. This goes through the mechanism I showed you, and you get the trans product. So you have a way to get the cis alkene, a way to get the trans alkene, or you can just use the same catalytic hydrogenation that we saw that works for alkenes to give you the alkane product. These same reaction conditions also work with alkynes to give you the alkane. So this catalytic hydrogenation works with alkynes or cis alkenes or trans alkenes to give you the alkane. Okay, so you have three separate hydrogenation products that can be obtained from an alkyne, and you'll just have to remember what they are. You know, each one is linked to a specific reaction, reagent, and conditions, and you'll just have to remember them. Okay, so I've gone over them in a way that I'm hoping will help you remember them and keep them straight in your mind. So this is the first set of reactions of alkynes. I'll end this video here, and we'll continue with the rest of the reactions of alkynes in the next video.